What's going on? So today is another episode where I will go ahead and talk about all of the classes that are available in the graduate program of computer science. If you haven't listened to this before, this is the very first video you're stepping into. This is attached to a playlist in which I talk about the process of going to grad school and how going to grad school is something that has a lot of things that goes into it before you even get the degree. And this is starting from already having a bachelor's degree. So if you don't have a bachelor's degree, you can still look at this. If you do, you don't have to use it. But the idea is to, for me, I'm trying to accomplish is to stay mindful about the things I'm trying to do each day. And focusing on explaining each one of these allows me to make sure I keep a good video, and then hopefully the information that the video I'm trying to produce provides some sort of value to someone else. This way, the value that I'm trying to give someone else, it tends to be good for me. You know, if I did this by myself, just talking, I think that I lose it somehow. You know, I lose the value and what I'm looking for. Anyway, I just wanted to go ahead and just say that. So basically today is computer architecture. It's one of the topics in computer science for systems, and it's computer science 502. And the topics that are covered include like instruction pipelines and memory cache to improve computer performance, instruction level, parallelism, machines, superscalar versus VLIW cache, and main memory hierarchy design trade-offs. Compiler optimization to speed pipelines, low-powered computer system design, processor, operating system, and compiler support. Graphics, DSP, and media processor design. This input-output system design, interconnections and networking, and introduction to parallel architecture. FPGA-based reconfigurable computing. Advanced topics, embedded processors, intelligent RAM, and superconducting computers. And basically the prerequisite is a course called CSE 345, which is, I'm just gonna look at it real quick. Oh, I can't seem to find it. So I don't see it up here. I think it's because I'm looking at the courses that are available for this semester, and if it's not available, it doesn't show up. So, so basically that's the course. Before I can go into computer architecture, I actually took a computer architecture course in undergraduate for Stony Brook. It was basically, and it's kind of just talks a lot about the low-level organization of everybody else. Actually, it wasn't computer architecture. It was computer organization, which was a class that was pretty. In order to understand computer architecture, computer organization is pretty important. It talked about like instruction sets. It talked about how certain processors, how the arithmetic logic unit works, basically how our computer actually works, the different types of architectures that are available. And it was a great survey for those things. And we actually did a project where we discussed, I think we were discussing like how certain architectures was being designed. So I guess we were supposed to look up a particular architecture and then talk about it in class. And it was a great course because the teacher was really interesting and fun to talk to. It was a little bit uncomfortable trying to absorb so much information, but I think that today I can look at the course after like 6-7 years ago, maybe 7 years ago. I can see that there's actually a lot of benefits from this. So I'm not going to go ahead and say too much about it. I'm going to just leave it the way it is. And the idea between computer architecture from Wikipedia states that In computer engineering, computer architecture is a set of rules and methods that describe the functionality, organization, and implementation of computer systems. Some definitions of architecture define it as describing the capabilities and programming model of a computer, but not a particular implementation. In other definitions, computer architecture involves instruction set architecture design, microarchitecture design, logic design, implementation. So there's a diagram here that kind of talks about how input-output happens in the CPU, and how the combinational logic is managed between main memory as well as how it goes through the entire processor and other registers. The idea between this is just to kind of explain to myself how all of these particular pieces are and what are required of you to kind of work on it. This will probably be another heavy class, because I think that one of the best ways to actually learn about these things would to actually be building a course, building a computer myself, which is something I actually want to go ahead and do. One of the reasons why I picked up a Raspberry Pi and I started to look at the course on Coursera. It's called Building a Modern Computer Using First Principles, from NAND to Tetris. So it talks about NAND is like the lowest level logic unit, and you can use NAND gates to kind of create different logical units. Like you can maybe make a AND or an XOR, and it's built on a very primitive application development system, where you kind of build your computer from on a software. You kind of build your computer using some sort of Java application that emulates the actual building of the chips and putting them together to create a computer. And the course is great. I think the actual course is bringing it up to NAND to Tetris. Okay, so NAND to Tetris is, I think it's .org. Yeah, NAND-to-Tetris.org. Yeah, so NAND-to-Tetris.org is provided by Noam Neeson and Shimon Shalkin, which from the Elements of Computing Systems. And one thing about the course is that if you don't have any experience with programming at all, and you don't have any experience with computers at all, the course is really it's free, it's open source, and it allows you to quickly understand the things you need before you're taking like a modern course. And I probably will take the second course. I had to finish this course, actually. I haven't finished it yet, to put the pieces together and to get an understanding on how to build on top of that. So what they do is they give you a foundation of building yourself your own computer, and then you can actually write software using any high-level language, Java, JavaScript, Python, C++, whatever, to build something like Tetris, what they're going to go ahead and do. And this is the thing I actually want to do with my degree, is I'm actually in search for finding it easy and entertaining to teach children, or to teach anyone that's interested in programming the basics without having to board them into the problems that are usually occur with building application systems. I think that I became a little bit overwhelmed. I still get pretty overwhelmed when a lot of terminology shows up on the page that you don't really understand quite quickly. And sometimes you might have some familiarity of it, but you don't necessarily have enough to kind of like talk about it on your own. So hopefully this course will provide some sort of clarity, and I'll be able to kind of learn certain things from it. But other than that, I think that's it. And I'm already over. Yes, this is already 10 minutes. It wasn't supposed to do that, but it was a lot to basically cover. And I think inside this video, I will go ahead and add a little bit more information into the description, so that way people who are interested in classes that are relative to Coursera's information is great. Being able to kind of find smaller pieces to play it on is great. So anyway, that's it. And the next episode is going to be on system operating systems. So stay tuned for that.